Let's discuss the electric field strength at the center of a uniformly charged hemispherical cup. Here we can see that this picture shows a hemispherical cup which is uniformly charged on the surface. It can be taken as a hollow hemisphere. It is of radius r, and its center at point C we are required to find the electric field strength. Now in this situation, to analyze it, we consider elemental strips on the surface of this hemisphere, say at an angular width theta from the axis of this hemisphere. We consider elemental strip which is having an angular width d theta. Say this is a strip which is in the shape of a ring. The width of this strip will be rd theta, as r is the radius and d theta is its angular width. And the radius of this strip, small r, can be written as r sine theta. So now in this situation, if we talk about the charge on this strip, that will depend on the surface charge density. Say if its surface is charged uniformly with a surface charge density sigma coulomb per meter square, then we can simply state the charge on elemental strip is, this can be written as dq, which is given by sigma multiplied by the area of this strip, which is its circumference multiplied by its width, that is 2 pi r sine theta multiplied by rd theta. Now due to this elemental charge dq, if we wish to find the electric field strength at C, it will be dE, as this result can be given by the direct result of electric field strength due to a ring on its axial point. The point is located at a distance r cos theta from the center of this ring, as this strip is in the shape of a ring. So this electric field, we can directly use the result of a ring on its axial point. So we can write electric field at C due to dq is dE, which can be given by k dq x, that is the distance we can use as r cos theta, divided by x square plus r square to power 3 by 2. So this will be r square cos square theta plus r square sin square theta to power 3 by 2. Now in this situation, you can see the result of elemental electric field due to this element can be given as k dq. We can substitute as sigma into 2 pi r square sin theta d theta multiplied by r cos theta, and in denominator we can write this as r square to power 3 by 2 is r cube. Here you can see this r cube gets cancelled out. If we substitute k as 1 by 4 pi epsilon naught, here pi and 2 also gets cancelled out, then this dE can be written as sigma by 2 epsilon naught multiplied by sin theta cos theta d theta. So this implies we can write down net electric field at C is, as net electric field we can write as integration of dE, which is sigma by 2 epsilon naught integration of the sin theta cos theta can also be written as sin 2 theta by 2 d theta, and for limits of integration for theta we can apply from 0 to pi by 2 for this complete hemisphere. This will be integrated from 0 to pi by 2. So here this final electric field will be sigma by 4 epsilon naught multiplied by this integration of sin 2 theta we can write as minus of cos 2 theta by 2, and its limits will substitute from 0 to pi by 2. If we substitute the limit pi by 2 over here, this will be minus of cos pi, that is minus 1, so it will become 1 by 2. We just substitute here, it is sigma by 4 epsilon naught So when we substitute pi, it is cos pi, so it is minus of minus 1, it is 1 by 2. Minus of when we substitute 0, it will be 1 by 2, this minus 1 by 2, which is 1 by 2 plus 1 by 2 is 1. So electric field at point C net is given by sigma by 4 epsilon naught, that is the final result. This you should again keep on your tips, that is the electric field due to a hollow hemisphere which is uniformly charged on its surface with a charge density sigma coulomb per meter square. It is given by sigma by 4 epsilon naught.